Okay. Okay, so I'm going to continue with the technique of partial fractions. We're still in that section. And today we're going to do more complicated cases and maybe even finish the section depending upon how I feel. Okay, so let us get started here. Okay, so partial fractions continued. Okay, so let's do just examples. So let's get a warm up on what we did last time. So suppose I have as an example, x to the sixth over x squared minus 1. How could we expand that in partial fractions? Well, this x squared minus 1 has degree smaller than the numerator, so we're going to have to perform some kind of long division to get the numerator to have smaller degree. So I'm going to divide x squared minus 1 into x to the sixth, and it gives me x to the fourth as the factor, and then we get x to the sixth minus x to the fourth. If we subtract, we get an x to the fourth. X squared minus 1 goes into x to the fourth, x squared times. And so we get x to the fourth minus x squared. We subtract, we get x squared. X squared minus 1 goes into x squared once. And then we subtract off x squared minus 1. We get a remainder. The remainder is 1. So that tells me that x squared, x to the 6 over x squared minus 1 is given by the expression x to the fourth plus x squared plus 1 plus the remainder, which is 1 divided by x squared minus 1, which we can think of as x to the fourth plus x squared plus 1 plus 1 over x minus 1 times x plus 1. And we have to find the partial fraction expansion of that second term appearing in what I just wrote. So let me do that over here. So we have 1 over x minus 1 times x plus 1. If you recall last time, is some number a over x minus 1 plus some number b over x plus 1 to be determined. So what we're going to do is multiply by the denominator on the left, both sides. We get 1 equals a times x minus 1 plus b times, a times x plus 1, I should say, and b times x minus 1. And now we choose test points. So I'm going to set x equal to 0 on both sides. I get 1, I'm sorry, so let's set not x equal to 0, but let's set x equal to 1, say. If we set x equal to 1, we get 2a equals 1. A is therefore 1/2. And if we set x equal to minus 1, we get minus 2b equals 1, so b equals minus 1/2, I believe. Okay, so the upshot of this calculation is that, let me write it all over here at the bottom, x to the sixth over x squared minus 1 is given by x to the fourth plus x squared plus 1 plus a over x minus 1, but a is 1/2, so 1/2 over x minus 1 plus negative 1/2 over x plus 1. And if we wanted to integrate this, we could now. I'm not going to do that. That was just a warm-up problem to do the partial fraction expansion. So let me clear the screen and let's talk about more complicated cases. Okay, so now we're in case 2 of partial fractions, where we have repeated linear factors. If you don't know what I mean by that, you'll see an example right now. So the example is this. What if we have something that's been factored as, say, 1 over x minus 1 squared times x plus 2. So this x minus 1 squared is a repeated linear factor. Okay, so the partial fraction expansion, when you have a repeated linear factor, looks a little different. For each repeated linear factor, you have to pay attention to the square. If it's a cube, it's going to be different. The number of repetitions matters. So in this particular case, we have a square, x minus 1 squared, so it's going to be a over x minus 1 plus b over x minus 1 squared. If there were an x minus 1 cubed here, you would have a third term with, say, c over x minus 1 cubed, but we don't have that. And then we have c, say, now over x plus 2. And that's going to be the partial fraction expansion. We'll have that form, but we have to solve for the a, b, and c. So how do we do that? We multiply both sides by the denominator on the left side. So we'll get 1 equals, what? So it's going to be a times x plus 2 plus b times x minus 1 squared. Oops, that's not correct what I wrote. I apologize. Let me start over. It's going to be a times x minus 1 times x plus 2 plus b times x plus 2 plus c times x minus 1 squared. Okay, and the way you solve this is by choosing test points, but you'll see you're going to run out of the obvious test points very quickly. So we can first of all here are my test points. I'm going to let x equal 1 for obvious reasons. I could also let x equal minus 2 for obvious reasons. And then there's we need 3 test points because we have a, b, and c. So I'm going to choose as my third test point x equals 0. There's no reason to choose it. It's just 0 is always a nice number to use if you can. So if we do x equals 1, we get 1 equals, the first term vanishes, and the last term vanishes. When x equals 1, you get 3b equals 1. That means that b is equal to 1/3. Okay, so that's easy enough. Now let's try setting x equal to minus 2. We get 1 equals, so the first term vanishes, the second term vanishes, and then minus 2 minus 1 squared gives me 9, so 9c equals 1, so c is a 9th. Okay, and now we have to stick in the third value of x. Okay, and then when x equals 0, you get 1 equals, okay, so what do you get? You're going to get x equals 0, you get a times minus 1 times 2, and then we're going to get b times x plus 2, so 2b, and then c times is plus c. And we know what a and b are, we know what a and c are, and from that we can solve for b. And I'll spare you the details. Well, maybe I will do the details. So we get minus 2a plus 2b plus c equals 1. And now I'm going to substitute the values of a and c. I'm sorry, b and c. So b is a third, so negative 2a plus 2/3 b plus 2/3, I'm sorry, plus 2/3, oops. Okay, so it's 2 times a third. That's 2b, and then c is a ninth, is equal to 1, and then you can solve for a. And if I did this right, let me circle the values we got. I think a becomes minus 1/9. So that means that we've solved for the partial fraction expansion. Let me, there's almost no room here, so let me save the screen and do some erasing. Okay, so we can rewrite this as negative a ninth over x minus 1 plus a third over x minus 1 squared plus a ninth over x plus 2. And each of these terms can be integrated using a u substitution in the obvious way. So I won't do it. I just wanted to show you. I'm just pointing out that it can be done. Okay. Okay, so let me give you another example, but we won't do the calculation. The problem is to write the form of the partial fraction expansion. Okay, so how do we, for the following expression, x cubed plus x over x cubed times 2x minus 1 squared times x plus 5. Okay, so this should be an x cubed, so let me make it obviously an x cubed. Okay, so the x cubed is a linear repeated factor 3 times, so you're going to get an a over x plus a b over x squared plus a c over x cubed. That's the contribution from that term. Now, the 2x minus 1 squared, 2x minus 1 is a linear factor. It's going to give you a d over 2x minus 1 plus an e over 2x minus 1 squared. And now the last term is an x plus 5. That's a linear factor. It's going to be an f over an x plus 5. So that's the answer to this exercise. I'm not going any further. The amount of algebra I would have to do to get A, B, C, D, E, and F would take me about 25 minutes, maybe even a half an hour. But this is the format of the answer. Okay, so let me summarize what we know so far. So if we have P of X over Q of X, and Q of X, and if the degree of P of X is smaller than the degree of Q of X, otherwise you would do a long division, then we each linear factor of the form, say ax plus b, which repeats a certain number of times, say k times, contributes the expression a1 over ax plus b plus a2 over ax plus b squared, etc., all the way up to a sub k. These are just numbers that you have to figure out, ax plus b to the kth power. Okay, to the and that contributes the expression to the partial fraction expansion. So that summarizes what we've done so far. Okay, so let's move on to the last case or which is the most complicated case, and we'll do a couple of problems hopefully. So case 3, irreducible. Let me write it like this: non-repeating, irreducible quadratic factors. Okay, so an example of what I mean by this is, let's take 1 over x minus 1 times x squared plus 1. The x squared plus 1 that appears here, this factor here, cannot be factored any further. It is an irreducible quadratic factor. And then the thing that you're supposed to do, and this is what works, is do the following. Well, the x minus 1 is going to contribute an a over x minus 1. And the other term, x squared plus 1, is not going to contribute a single number. It's going to contribute a linear expression, bx plus c, to the partial fraction expansion. Okay, now from this we can figure out a, b, and c in the same way as before, except that you're going to have to choose other test points. So if we multiply both sides by the denominator on the left, we get a times x squared plus 1 plus bx plus c times x minus 1. So I'm going to choose the following test points. I'm going to choose x equal, first of all, 1. And if x equals 1, then we get 1 equals, well, the second term vanishes on the right. And the first term gives me a 2a. So that means that a equals 1/2. Let me circle that or box that off. Okay. We can also let x equal 0. I mean, I'm just choosing a small integer number. If we let x equal 0, then we get 1 equals a plus bx plus c, in this case is c, times minus 1. So that tells me that if we solve, we see that c equals a minus 1. And then a is a half. So that's a half minus 1, which is minus a half. So c equals minus a half, according to this. Okay. Now, we still have to solve for b, and I'm going to choose another value that's an integer close to 0, maybe x equals minus 1. You can choose x equals 2 if you want. It doesn't really matter. So then we get 1 equals 2a. Minus 1 squared is 1, plus 1 is 2, plus negative b plus c times minus 2. And so what do we get? We're going to get, this is 2a, so it's 2a is a half, we said, so 2 times a half, plus 2b, which we're trying to figure out, minus 2c, but c is minus a half. So what do we get? We get 1 plus 1 is 2. So it looks like if I did this correctly, I'm hoping I did this correctly, we get 2, so 1 plus 1 is 2. So 2b plus 2 is equal to 1. So that means that b is minus a half. So, okay. All right. So so we now have the terms a, b, and c, and I'm going to integrate this expression. I'm going to show you it can be integrated. So let me save the screen and then clear it. So what do we know now? If we want to integrate dx over over x minus 1 times x squared plus 1. It's the same thing as the integral of a, which is a half over x minus 1 dx, plus bx plus c, but b is minus a half and c is minus a half. So it's minus a half x minus a half dx over x squared plus 1. Okay, so let's try to integrate this. Now, the first term is 1/2 dx over x minus 1. Now, the integral on the second integral on the right is, I can break it up, the numerator of the fraction, and it becomes two fractions, and I can bring the constants out. And what I get is minus a half the integral of x dx over x squared plus 1. That's one of the integrals. And the other integral is minus a half dx over, let me write it as 1 plus x squared. I have a reason for that. Okay. So now the first integral is 1/2 ln absolute value of x minus 1. The last integral is negative a half the arctangent, because the derivative of arctangent is 1 over 1 plus x squared. So, okay. And it's just the integral in the middle which we need to do. And the integral in the middle is given by a u substitution. We can let u equal x squared plus 1, then du equals 2x dx. But so therefore 1/2 du is x dx, and the integral of x dx over x squared plus 1 is given by 1/2 the integral of du over u, which is 1/2 ln absolute value of u plus c, which is 1/2 ln x squared plus 1. You don't need an absolute value for that, plus c. Okay, so now we can go back and substitute what we just got into the expression to get. So we have a minus 1/2. We have to incorporate with the 1/2. So you're going to get a minus a quarter ln x squared plus 1. And that's the answer to our problem. We've now computed the entire integral, this integral over here. So that's kind of cool. I'm pretty happy about that. Okay. So I think we did quite a bit of algebra in this video. Even though it's not a long video, it is very, very tedious to do a lot of algebra. So I think this is good enough for today. I'll continue with some examples next time of this technique, but I won't be, there's not much to teach anymore about it. We just have to do some examples to practice. So, au revoir.